I'm Ethan, the ESR of Marie Curie ITN project 5G Worlds. The topic of this presentation is a study of angular stationarity of 5G millimeter wave channel. Here is the outline of the content. First, let's have a look at the directional propagated millimeter wave channel. Due to the high attenuation of millimeter wave signal, which could up to 100 GHz, the beamforming is widely accepted as an enabled technique in millimeter wave communication. Both TX and RX use the beamforming technique to cast a narrow beam to each other in the communication as the figure in right-hand side. Therefore, the millimeter wave channel is very different from the current 3G and 4G channels. We can see that the signal in 3G and 4G channels are omnidirectional propagated to the user as in the figure at left-hand side. However, in millimeter wave communication, the signals are directional propagated. So, in the research of millimeter wave channels, the study of the directional propagated channel property is very important. In the second part, I will introduce a method to calculate the angular stationarity of directional channels. This method is the extension of the former study of stationarity of the channel in time, frequency, and spatial domains. At the moment, we only focus on the azimuth angular stationarity. Assume there are directional impulse responses measured at a position of a channel environment, and we illustrate them along azimuth axis. We also assume there are n-directional impulse responses form a sliding window, and the sliding window can be moved along the azimuth angles, like the plot at left-hand side. If we average the power of n-directional impulse responses at the average PDP in each sliding window, we can calculate the correlation coefficients between the average PDP in the first sliding window and the average PDP in other sliding windows. Then the correlation coefficients can be calculated like the plot at right-hand side. If we decide the threshold and we say for the correlation coefficient above the threshold, we consider the sliding window is moving inside the angular stationary region. Otherwise, it is moving outside the angular stationary region. In this part, I will show some results about the angular stationarity studies of a channel environment. We have measured a channel in an indoor office environment. Both TX and RX are using 25 dBi gain Hall antennas, working at 6 GHz. The 3 dB beam width is 10 degrees. The positions for TX and RX are illustrated in the figure. During the measurement, TX rotates the Hall antenna from 0 degree to 355 degrees in azimuth angles, while RX Hall antenna was holding still, pointing to the TX all the time. The figure at the left-hand side is angular correlation coefficients between the average PDP in the sliding window at 0 degree azimuth angle and the average PDP in the sliding windows at other azimuth angles. If we decide the threshold at 0.8, then we can see the angular stationary region is about 75 degrees. We simply use the procedure to calculate the angular stationary region in other azimuth angles and keep using the threshold at 0.8. The estimated angular stationary region of millimeter wave channel in different azimuth angles can be found in the figure at the right-hand side. We can see that there could be three types of angular stationary regions. Type 1 is very large, Type 2 is very small, and Type 3 is in the middle. We also estimated the root mean square delay spread and the K factor based on those directional PDPs in azimuth angles. We found a pattern that for the directional PDPs in the azimuth angles of Type 1, the root mean square delay spread is very small. The K factor are very large. While for the directional PDPs in the azimuth angles of Type 2, the root mean square delay spread is very large and the K factor are very small. For the directional PDPs in the azimuth angle of Type 3, those statistic properties are in the middle. If we check the directional PDP of Type 1, they normally contain one strong light-side component and two weak nanoside components. They account for high K factor and small root mean square delay spread. Those in Type 2 normally contain one fairly weak nanoside component. They doesn't have significant power above the noise floor. This could explain the very low K factor and the dramatically changed root mean square delay spread. Those in Type 3 normally contain one relatively strong nanoside component and a few weak nanoside components. They account for those 36 parameters in the middle. Here we come to the conclusion. The study of angular stationarity region is introduced as a method to help us to understand the property of the directional minimum channels. Based on the result of angular stationarity region, root mean square delay spread and k-factor are estimated. Those results can mutually explain the estimated statistical parameters of measured directional millimeter wave channels. Three types of directional millimeter wave channels are found. Those could reflect the different propagation situations of the directional millimeter wave channel in different azimuth angles, such as the existence of the left-side path between Tx and Rx, and the power gain of nanoside path. Thank you very much for watching.